Good morning. My name is Aaron Frankel, and I'm responsible for marketing our manufacturing engineering solutions.
And I'm Scott Felber, and I'm responsible for marketing our product design solutions, along with Paul Bevan, who will be doing the live demos today.
And this morning, we wanted to explore with you, through a demonstration, how digitalization and our smart innovation portfolio transforms design and manufacturing. But even more so than that, how it enables us, empowers us to reimagine products as well as reignites our imagination. See, as designers and manufacturers and engineers, we're all trained to think that the way we make products and the materials we make them out of dictates how they're designed, distributed, and serviced. And it's this way of conventional thinking that is constraining our potential as innovators and as businesses. It constrains how far and fast we can travel. It constrains how well our products match our personal needs, how much energy we consume when we run our products, and how much it costs, and how quickly we're able to deliver on innovation. And you can see that effect in this part. This is a simple part. It's machined out of a solid piece of metal. And you can tell from the planar faces, the pockets that have been removed from that block of metal, and the ribs that are still there. And when you make parts this way, the problem is you end up leaving excess material, and this increases its weight. We also constrain its shape and its strength, and this is what limits our product performance. Conventional thinking also limits our performance in manufacturing. To make this part could require as many as 2 CNC machines, 7 different operations, numerous cutting tools. And all of this adds up to time and cost.
Now is the time to rethink everything, and we believe now is the time to adopt additive manufacturing. With additive manufacturing, we can now create new designs that are lighter, stronger, and never before have been envisioned, and we can manufacture them in an agile, cost-effective process.
Here we're comparing the difference between conventional machining and additive manufacturing. On the left, you can see conventional thinking. This is a block of material that's been set up on a machine tool, for example, in a couple different orientations. And you can see the different machining operations. You can see the drilling operations, drilling the holes. You can see machining operations, removing material, so we end up with this final target shape of this part that we're trying to produce. Now, on the right-hand side, you're looking at additive manufacturing. Here we're able to produce a part in a single setup. The shape of the final part is very unique. It's very organic looking, something that we couldn't have been able to manufacture using a CNC machine tool. And on the inside of this part, you can see a honeycomb lattice-like structure where we've been able to take out a lot of material while still maintaining the structural strength of this particular component. And it's these new types of disruptive, innovative technologies that are really going to change products forever. It's time for us to start rethinking everything. This aircraft was designed over a decade ago by one of our customers, One Aviation, who thought differently about air travel. So using the latest technology available to them at that time, they pioneered a new class of jets, the very light jet. And aerospace engineers used NX for modeling, human-driven calculations, supplemented by CAE simulation optimizations to design a very lightweight, cost-effective, high-performing jet. But we've wondered, what if we could redesign this jet using the technologies available to us today? What would it look like? Now, we don't have the luxury to redesign this entire jet today, but we can zoom in and we'll just look at one component, one part of this aircraft, the elevator bell crank in the very rear of the tail. And this is a critical component to the control systems of this aircraft. This component basically connects the actuation of the pilot's joystick mechanically to the elevators in the back of the aircraft that control its pitch. And so let's have a little bit of fun. Let's try to break through some barriers. Let's apply additive manufacturing to reimagine this bell crank and try to design it lighter, maybe even stronger, and do so that we can increase the payload of this aircraft. Maybe we can now take an extra passenger on board with us when we go on a trip.
So as engineers, what we do today is we set up requirements and goals using analytical methods to help us define the physics that govern product performance. We use tools like Excel, intellectual property, prior knowledge, and even Google to set up these calculations. The problem with these calculations is they're not tied directly to the geometry which they need to create. So we believe there's a better way to do that. And what we want to do is take all that math now and directly tie it into the geometry which it's going to need to create. So what we have Paul now working on a change request. And what Paul's going to do is using Active Workspace embedded in an X. Being a designer every day, he doesn't have to go to another tool. It's right there. He has access to all the information he needs. The request here is he wants to lighten up the elevator bell crank. So as he digs down through the information that was sent to him, he's going to come across the set of equations and math that dictates the performance for this part. He's going to go ahead and launch that part directly from inside of his CAD tool into the Symbolica tool, which is the rich math engine which we can set up all these calculations we need to do. And within Symbolica, it has the step-by-step processes of everything Paul needs to accomplish, and he can go ahead and look at it. It has all the pictures and images pulled from CAD so he can get a nice view of what he needs to do. What he's going to notice is it might be a little out of date, so he's going to quickly recalculate the entire set of equations at this point in time. And as you look at that, if you can see somewhere along the way, all the numbers that are there and all the text that's in italics are all live equations. At any point, Paul could pick on those, change values, interrogate them. Also, on the left-hand side, he has the table list of all his variables and their present values. And on the bottom, you can see all the rich math functions that can easily put into Symbolica. And if anybody's tried to do high-level math with Excel before, you know how hard that can be to do. And the other nice thing, as Paul increases the mass at takeoff here by a couple hundred kilograms and recalculates everything, the beauty of having Symbolica now is I can use these values and tie them directly into CAD. And it's bidirectional. I can push these values into my CAD models, and as I change my CAD models, the values can come back here to retrigger all those calculations. So we can see now, when Paul increases the mass at takeoff, he now has to worry about having a reactive force on the elevator bell crank of about 1,000 newtons. And we'll use that number later on in the next demonstration. So really what we have now is we have intelligent models that can unleash our engineering potential within our organization. We can tie it all together. The next step we're going to do is we're going to do optimize. And today's optimization usually occurs after an initial design has been created to get an incrementally better model. And this optimization is usually performed by a CAE analyst using specialized tools after initial design. But this might not be the best way to do it, because these optimization routines can be biased. And they can be biased by many things. One is the existing geometry we started with. Number two is the not invented here syndrome, and even the emotional attachment people have to their designs. So what we want to do is use the power of the computer and be able to take now the optimization and give it to the designers early on in the initial design phase during ideation, where these biases can be eliminated. Because the computer has no bias about existing design. It's just going to do what we ask it to do. So what we want to do now is we want to go back to the demo. And what Paul's going to do in the next one, he's opened up the entire elevator assembly. And he's going to focus in on the area of the elevator bell crank. And what he's going to do, in this case, like Aaron talked about before, we're going to imagine a brand new design. So what he's going to do now, he has some stuff set up to run the optimization here, because we have to kind of tell it what we want to do. And when Paul goes into that area now for the optimization, he needs to set up a design area. He needs to set up material types. He can add symmetry to it. And the one he's going to do here now, he's going to go ahead and manage the optimization features. And that's really, within this design space, what are the areas we need geometry to stay, and where can we take geometry out of? For instance, a couple of these areas he has holes where there's going to be pins, and a couple other areas we need material around the holes, which to put the other pins in. And then he's going to manage the load cases, which were calculated before using Symbolica. So Paul's going to go in here now and make sure all our loads are all set up. And once that's all done, he's going to go ahead and he's going to run the optimization as a designer now, not as a CAE analyst. So let's think about optimization for a second, really, because to optimize means to make perfect. So what Paul's doing now is he's making the perfect design based on the inputs he gave it. And what does really to make perfect mean? One customer once told me, really, a perfect design is like this. Anyone can build a bridge, but only an engineer can build a bridge that'll barely stay standing. That means it's perfect, right? You use the minimum amount of materials to get the maximum amount of gain. The other thing what it's doing behind the scenes here, as Paul's doing, is it's generating multiple designs and multiple iterations and running through all the solutions it can do. And it's going to give us back the best solution it can do. One thing we'll notice when we're done is, remember the original part that Aaron showed? The original elevator bell crank, it had a kind of a stress path that went along this way. And when we get the new design, you'll kind of see how it maybe is a little bit different. So the design's all complete now, so now we're going to go ahead and we'll go look at what kind of shape we came up with. And when we go ahead and look at the design, not only do we talk about which way the stress is going to go through that part and where it's going to bear all the weight, the other thing I want people to notice too is based on that set of inputs that we originally calculated before using Symbolica and knowing what we know today about conventional design, would anybody ever design a part that looks like this? No, we wouldn't. And it looks very organic like we said. Now we can optimize designs for the new generation of products. And although these designs are perfect, they still may need to be adapted a little bit.
Innovation's a team sport, and this means that we need to use tools that give us the freedom to be able to combine and adapt our ideas that are generated by the computer, and other ideas generated in our enterprise, and be able to combine all those together and turn them into a remarkable product. Traditionally, engineering software tools have evolved in silos based on disciplines, and they're built on data models and different specific geometry types. And these applications tend to be optimized separately based on the way that the specialists intend to use the tools. And the problem is that these tools don't work on the same data. And this means that we're either having to convert models between applications or even remodel something if we want to try to improve it. And this is what's limiting our potential because it's slowing down innovation. And so our breakthrough is to provide the next generation of modeling tools, Convergent Modeling, that allows us to work on mixed data types all in the same application so that we can innovate faster. So here we're looking at NX. And this is that faceted model that we had optimized for strength and weight. And Paul's going to do something quite remarkable that's not possible with traditional CAD tools. He's going to use the NX shape design applications to create a precise surface in an area where we believe we need to add a little bit of material. Now, we didn't optimize this part for how well it's going to be able to flow through the factory floor and potentially withstand somebody accidentally knocking it against a piece of equipment. And so we felt in order to make it absolutely perfect, based on our experience, we needed to add a little bit of material. And NX is providing us the power to be able to do this. Beyond that, we're seeing an increased use of faceted geometry with different shape-based simulation optimization tools, as well as models that we're getting from scanning equipment. that could scan a physical product that we might need to reverse engineer, or even from CT or MRI scanners that are scanning our anatomy so that we can design better implants. And because we have these powerful tools now, all inside one application where we can easily model in a mixed geometry setting, we're able to innovate faster. And you can even start to see what's going to happen in the horizon. We're going to be able to have the ability to not only model just geometry, but we're able to model different types of materials all combined into a single part. Someday providing us the ability to mix materials in a part so that we could even add sensors directly inside of these parts and then have them printed so we can measure their performance. And the breakthrough here is now we're free to imagine what's possible.
So today validation occurs when we run computer simulations on the existing geometry to make sure that the results we get are the ones we really want. But as we move forward to these new methods, there's even going to be a bigger emphasis on this step of validation. Because as we make these new kind of shapes, there's going to be a lot of people who do not believe they will perform as well as the existing shapes they were trained to build. So as this becomes more and more critical, we need to look at all the steps of validation. So what we want to do now is we want to show how we can then take the information we have from the existing parts and validate them and prove out our hypothesis that the parts are now better. So what Paul has now here, he has the brand new part in NX. We're going to do some 3D analysis on it, and we're going to start by looking at the deflection on the part. He's going to apply he's going to open the results from the original part that we still have around, and we're going to compare the results. One thing that's not been noticed through here is this part's about a little less than 20% lighter than the original part, too. And what he has here now is he has two windows open, and in the second window, we're going to put the old part, and in the one window, we're going to put the brand new part. And then we're going to synchronize the view so we can kind of see what's going on. And the first thing we'll look at is we'll look at the deflections. And Paul's just going to drag a template for the deflections right onto both parts. And we can get the deflection where we expect it to be along the pinned area. But the real interesting comes in now when we start looking at the stress and how these parts were designed and how they're going to have to be manufactured. So when we apply the stress to both windows, we look, the stress on the brand new part is over 90,000 megapascals. And we'll address that in a little bit. And on the new part, the stress is lower than that, on the original part. But if we look at the original part, which is the one on the right, you notice along the ribs we have a lot of residual stress. And traditionally, as a CAE analyst looking at data like this, we'll look at these parts and say, yeah, there's that stress in there, and over time that might have some effect on the longevity of the part and how long it lasts. But you know what? I can live with that stress. But if we go ahead and look at the brand new design now, we don't see any residual stress at all in the part. All the residual stress has been removed due to making it through optimization. But if we want to take it one step further and kind of compare apples and apples, because if you notice now the scales aren't the same on both, what we'll do is we'll apply the exact same scaling for the stress to both parts. And we can see now that that stress is really concentrated just in that little bit of knockout on the back where we had to pin that thing. And we have more area in there. So really what we would do now is we would go back and use those adapt techniques that we had before to, again, add some material here and reanalyze this part to even eliminate all of that stress. Then we'll have almost practically a stress-free part. And then we can show everyone, yes, we can meet the criteria we're looking for. So the breakthrough here now is that we can embrace the shape of things to come.
So now that we've designed and validated the performance of this part, it's time to make it. And manufacturing is where companies make or break their business. So to compete, manufacturers need to deliver on innovation faster, drive down costs, and do all of this while delivering nothing but perfection. When we talk to a lot of companies, we often hear how companies are trying to improve the performance of their business by annual incremental improvements. And unfortunately, we believe that this way is a bit limiting. So we also hear from a few companies that are adopting more disruptive innovation types of approaches, like additive manufacturing, that can enable them to leapfrog over the competition, similar companies in their same class. So we believe it's important to start retooling manufacturing and start adopting these types of disruptive additive manufacturing types of approaches. What you're looking at here is our optimized part inside of NX, and we're going to use an application that we've been working on with a partner, DMG Mori, one of the world's largest machine tool manufacturers. It's an application that we can use to not only do 5-axis CNC programming on a machine tool, but this machine has been equipped with additive manufacturing capabilities. And what Paul is showing you here is that we've subdivided this model into its regions that we need to go ahead and build. And we'll go ahead and take this into the machining environment. So we've set this part up on our hybrid machine tool that combines both CNC machining and additive manufacturing capabilities. And we've created the tool paths. Now what we're going to do is we're going to run through a simulation to be able to visualize the deposition of material. Now the way this machine works is this machine is equipped with a nozzle that blows metal powder and then uses a laser beam to sinter, to basically fuse that metal, weld that metal into a solid shape. And what you're seeing here is our optimized approach to grow this part. We take into consideration how this part is going to be heated and cooled, and how that expansion, that thermal expansion, is going to affect the performance of what this part's going to look like. Now, as we continue to visualize what this part is going to look like as it grows, we can get a good idea that its surface finish is going to be rather coarse, which is what we would end up with. And if you go next door to the showcase, we have some examples of parts that have been built on this DMG Mori 5-axis machine, comparing the surface finish of something that we've printed and something that we've actually machined. Once we've finished doing the printing of this part, we can then switch the tools, and we can use and take advantage of the very precise 5-axis machining precision of a very high-end CNC machine tool in order to machine the surfaces to the exact tolerances and the surface finishes we're going to need to be able to have an effective product. And here you're basically looking at a simulation of the material removal. You get an idea of how we would machine this part to get that desired end result. Now, additive manufacturing also affords us a completely new level of flexibility. These types of machines don't have large footprints. They're able to combine together multiple operations that could require a number of machines to be able to produce parts like this into a small area of the shop floor. And we could have these types of machines strategically placed all around the globe. So if we had to go service our aircraft someplace, we'd be able to print a part where we needed it. So let's say we had to service this aircraft, and we had to replace this part. And this aircraft happened to be on the other side of the planet, where we didn't have a DMG Mori machine tool, but maybe we had a powder bed machine tool. Now we can tap into our digital inventory of parts and pull out that design in the location where we have this powder bed machine where we need to service that aircraft. And we've already adapted its design for the way that we're going to need to be able to manufacture it. We've set it up on the build tray of a powder bed machine. We've designed in the support structures that are going to have to hold it into place. And we need support structures because the way that a powder bed machine works is it basically spreads a very thin blanket of metal powder across the bed, and then we use a laser in one direction to fuse that metal into shape, and we basically end up growing these parts vertically. So we have to be able to somehow orient and hold them into place. We've designed in the support structures. We've done the planar slicing and the hatching that is going to control where this laser beam needs to go in order to grow our part right there on this machine on the other side of the plant. And then the next step of the process would be to clean off the support structures, and then we'd be able to service our aircraft. And so this way of manufacturing enables us to manufacture and make products in a new way and unleash our potential, not only in manufacturing, but also in design. And so now we have the power to reimagine the products of the future. And the time is now. Thank you.